Hello, everyone. Today's worksheet focuses on 4 topics. The first 3 of which are pretty related, and the fourth is its own. Well, it's related to the other 3, but less transparently. So those topics are maximum likelihood estimation, naive Bayes, Laplace smoothing, and then neural networks. So before I get into the problems, I'm going to just give my brief summary of what's up with these 4 things. So first of all, what's maximum likelihood estimation? I'll give you an example. So suppose that you see a bunch of coin flips, and here's what the coin flips are. They're heads, heads, tails, heads, tails, heads, heads, tails, tails, heads, 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 heads. That's the sequence that you see. Maximum likelihood estimation is a way of estimating how the sequence was generated. So suppose you assume that the coin flips are independent, and there's just some probability of getting heads and some probability of getting tails. So independent and prob p of heads, prob 1 minus p of tails, which I guess we're just writing as a capital T. There's this thing called the likelihood function. And the likelihood function of some of the parameter p of this model, right? Because this is if p was 0.3, that would be one model. If p was 0.99, that would be a different model, right? So p is kind of a parameter of this model that determines which model we have, is another way to think about it. The likelihood function of p is just equal to the probability of the data given that value of p. So if you have that value of p, how probable is your data? Now, what is maximum likelihood estimation? It's a way of getting a value of p, and what you do is you get the arg max over p of likelihood p. So that just means the value of p that maximizes the likelihood. That's what maximum likelihood estimation is. You can do math to figure out what it is. But in this case, the maximum likelihood estimator is just like number of heads divided by number of tails. Or sorry, number of heads divided by the total. So in this case, PML, so the maximum likelihood estimate of P, is equal to, well, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 heads, divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that's maximum likelihood estimation. All right, I'll next go to naive Bayes, and then Laplace smoothing. Laplace smoothing is actually a little bit more related to maximum likelihood, but this is the order I presented things in. So I'll make this really small, and we can make it, we can bring it up again. Okay, so what's naive Bayes? So naive Bayes is a way of making predictions. So it's a predictor. So you're imagining you have some features, right? F1 through Fn of some data. So these features could be like, you have a house and it has some, it's got a zip code and it has a number of bathrooms and a number of bedrooms, and it's got a certain area of all the floors and such, that kind of thing. It could be, if you have a document, it could be like the number of times the word apple is used, number of times the word money is used, number of times the word free is used, number of times the word science is used, say. So you have some features or some data and some specific point that you're interested in. And you also have class. So class Y, and that you want to predict. So this is something that you don't know. Like for instance, in the case of a house, maybe you don't know how much you could sell it for. Or in the case of a document, you might not know whether or not it's spam because you're a little computer program, and you want to figure out whether to show it to a human, but you don't want to show the human spam. So in this case, what we're going to assume is that we have probabilities. Probability that feature I has some value fi given the class values. So for all fi and y, for all I, fi, and y, actually. So we're saying that for each class value, we know, like if you were spam, we know the probability that you would have the word money in the document 3 times. Or if your house could sell for a lot, we know the probability that it would have like a really large, that it would cover a really large area. And then we can just use like Bayes' theorem to get some kind of prediction. So what we would do is we would say that we have some posterior distribution. So there's probability of y given that feature 1 has value f1 and feature n has value fn. Well, and when I say we use Bayes' theorem, I really just mean we use sort of normal conditional probability. So this is, by the definition of conditional probability, which is kind of the same as Bayes' theorem, but whatever. So it's probability of y and f1 equals f1 through fn equals fn divided by probability of f1 equals f1, fn equals fn, right? So we have this fraction. It's got a numerator and it's got a denominator, but we're going to ignore the denominator, and I'm going to tell you why. Because what we're interested in is we're interested in the most likely class. We just want to predict the most likely things. So we're taking arg max over y. Y equals little y. Okay. So the reason we're doing that is we want to get the most probable class. Now, so in the second line, we want to get the y that maximizes this fraction, but the denominator doesn't depend on y, and it's positive. So we can basically just ignore the denominator in this term because it doesn't affect what the maximum value of y is going to be. So we'll just erase it and move the numerator down right here. Okay, so far this has just been normal kind of standard math. Now I'm going to do something that's a little bit strange. It's a little bit unusual, but it's going to be okay. What I'm doing is I'm saying, and here we're getting more into the Bayes. We're saying that this is arg max. I'll do it in 2 steps. Probability that y equals y times probability that f1 equals little f1 through to fn equals little fn, given that y equals y. Again, this is just a conditional probability, but now I'm going to do something really strange. I'm going to say it's equal to arg max over little y, probability that big Y equals little y. So the label is this particular little y label, times the product from I equals 1 maybe you've seen this symbol for a product before. It's like a big capital pi. So from I equals 1 to n, the product of the probability that each feature has its observed value given that class. So what we're saying is the probability that feature 1 has value f1, feature 2 has value f2, given that y equals y, is like the product of the conditional probabilities. So that means that feature 1, feature 2 through feature n, they're all independent, given the value of y. So if you were to draw that in a BaseNet, that would look like you have this node y, and one child is f1, one child is f2, and all the way through a child that's fn. So in the case of spam, what we're saying is that given that you're spam, knowing the number of times I say the word money doesn't tell you anything about the number of times that I say the word free. Or in the case of house prices, what we're saying is that given that you know how expensive a house is, knowing how much area it takes up doesn't tell you anything about how many bathrooms it has. So this is basically always wrong. But the question is, how wrong is it? Like in the case of spam, you know, maybe it's like not too bad of an assumption. In the case of house prices, it's pretty wrong because like the way you come up with a house price is by saying, okay, how good is how much area is it? Is it in a nice neighborhood? How many bathrooms does it have? And you're sort of counting up all of those factors. So like if you know a house price is like middle tier, for instance, and you learn that it has like a really it lives in a really nice neighborhood. Well, if it's in a really nice neighborhood and it's mid-tier, then you know, oh man, all the other things must be bad about it. So that's a case where you wouldn't want to use naive Bayes. And yeah, we call it naive because it's not using all the information it could, but it's often like a decent job. So that's naive Bayes. And I'll just get rid of that. We'll talk more about that later. So now I want to talk about Laplace smoothing. So if you remember this maximum likelihood thing with the heads and the tails, right? We saw what happened with that sequence of heads, tails, heads, tails, heads, heads, tails, tails, heads, 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 heads. But let's say we saw another sequence, right? Let's say what we saw was heads, heads. That's it. We don't see any more. We just see two heads. So the maximum likelihood estimate of the probability of heads is 1, right? Because if we were certain to flip a heads, then we would be certain to get heads heads if we flipped the coin twice. But you know, if we were only 75% sure to get a heads each time, we would be less than certain to get 2 heads in a row. So the maximum likelihood estimate says that there's probability of 1 of heads, and so if and so you can just be sure that there are going to be heads forever. You can be absolutely certain. And that's not really right, is it? Like that doesn't really make sense. You wouldn't want to bet your life on the third coin being a head. So Laplace smoothing is a way of kind of adjusting the way you do this estimate to be a little bit more unsure, to hedge its bets a little bit. And it has, I'll tell you, this actually has some connections with Bayes' theorem, which you should kind of expect because, like, you know, a priori, it's like not that likely that the coin is like definitely 1. So you're somehow using your prior knowledge, which is related to the prior distribution in Bayes' theorem. But I won't go into the connection right now. I just want to let you know that it exists so that on your own time you can find it out. So what we do in Laplace smoothing is we say that probability Laplace of heads given some parameter k. So Laplace smoothing, it has this parameter k, what it is it says, okay, we've got 2 heads plus k divided by, we saw 2 heads plus k plus 0 tails that we saw plus another k. So it's 2 plus k divided by 2 plus 2k. And the way you can think about it is that Laplace smoothing is saying that, oh, imagine before, like you didn't just see these 2 heads. You also, in red I'll write down things that didn't actually happen, but you're imagining, right? You also saw k heads and also k tails. And then you're getting the proportion from that. So supposing that k equals 1, right? So in this case, the probability using Laplace smoothing of heads, given that k equals 1. So 2 plus 1 is 3, and 2 plus 1 plus 1 is 4. So that would say you've got a 75% chance of seeing another head, which makes a little bit more sense, right? Like it's a little bit less. It's not so totally dogmatic, but it's also not clearly heads. If you had to bet whether it would be heads or tails, you would want to bet heads, right? Because that's what we've seen before. So that's what happens if k is 1. And to just give you a sense of how it depends on k, suppose k was 0.01, right? So probability Laplace of heads with 0.01, well, that would be 2.001 divided by 2.002. Now, what's that actually equal to? The simple answer is it's quite small, but it does actually come out to a number. Where's my calculator? My calculator is not coming up on the screen, but you'll have to trust me that this is approximately equal to 1. So if k is really small, then this is doing basically the same thing as maximum likelihood. And where small means small compared to the number of things you've seen. What if k is really big? So what's probability Laplace of h given 1,000? So that would be equal to 2 plus 1,000 is 1,002 divided by 2 plus 1,000 plus 1,000. So that's 2,002. So that's approximately equal to 1/2. So if k is really big, then you're saying that like, oh, it's 50-50. I don't know anything about what the actual frequencies are. I'm just going to go with an uninformative prior opinion. So that's Laplace smoothing. All right, so now we'll get on to neural networks. What can I say about neural networks? So they've only just been introduced. Hopefully you've got a bit of a sense of how they work from doing the programming assignment. But basically, what we're doing is a neural network is supposed to map some input, which is a vector, to an output, which is a vector. And we assume that we have lots of input-output pairs. So what do we do? What do we do with neural networks? Well, basically, it turns out that they're a way of providing it's a very expressive way of kind of having parameterized functions, right? So like imagine the way you wanted to do it. Suppose you had one input and one output. And suppose how you were going to do it is you were going to use a linear function to predict the output from the input. And your points were this, 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 this. right? If you had to use a linear function, then I don't know, I guess you would pick like this line or something. It just like wouldn't be a very good expression. It would be nicer if you could do something like boo, 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 right? If you could express a function like that, then you would be like a lot better able to fit this data. So that's what neural networks do. They're a way of expressing a lot of functions. And also it turns out you can train them. If you have data, you can train a neural network that mimics that data. Like on the inputs, it like gives you the right outputs. So that's the very basics of it. We'll get into it a little bit more. So now let's start the actual problems. So naive Bayes. So in this question, we're training a naive Bayes classifier. And you have class labels Y, and the input functions are A and B, and they're all binary features. They all have domains 0 and 1. And we have these 10 training points. Okay. So first, what's the maximum likelihood estimates for the probability of Y, probability of A given Y, and probability of B given Y? Well, so to do this, we just say, okay, we have 10 training points. So this is something divided by 10. And how many of them is Y0? Well, there's 1, 2, 3, 4, 5, 6. So 6 out of 10, which is the same as 3 out of 5, right? Now, how many of them were 1? Well, if 3/5 of them were 0, then the rest are 1. That's 2/5. Okay. Now, what's probability that A is 0 when Y, given that Y is 0? So how many times is Y 0? So it's this row, this row, this row, this row, this row, this row. That's out of 6. And how many of these is A 0? Well, it's this one, and that's it. So 1 out of 6. That's our maximum likelihood estimate of this. All right. What's the probability that A is 1 given that Y is 0? Well, it's all the other times, right? So it must be 5 out of 6. Because given that Y is 0, probability that A is 0 plus probability that A is 1 has to add up to 1. And indeed, you see this one, this one, this one, this one, this one is 5. All right, what about the probability that A is 0 given that Y is 1? Well, here's Y1, 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 Y1. That's where they are. And we see in this one, A is 0. So that's 1 out of the 4 cases. 1 out of 4. Now, what's the probability that A is 1 given that Y is 1? Well, it's the other 3, right? Here, here, here. So that's 3 times A is 1 out of the 4 times that Y is 1. All right, now we're looking at probabilities of B for B, given the values of Y. So given that Y is 0 here, where is B 0? So B is 0 right here, and it's 0 here, and in none other of these. So that's 2 out of 6 cases. So that's 1 out of 3. That's our maximum likelihood estimate for that probability. Well, what's our probability that B is 1 given that Y is 0? That's equal to, well, it's just 2 out of 3, right? Because probabilities have to add up to 1. In particular, given what you're conditioning on, probabilities of all the possible outcomes have to add to 1. Okay, what about if we condition on Y being 1? So now we're looking at this row, this row, this row, this row. Well, there's 1, 0. And there's a 1 here. Oh, that's not one of our rows. A 1 here and a 1 here. So it's a 1 in 4 chance of a 0 and a 3 in 4 chance of a 1. Okay, so suppose we have a new data point. A is 1 and B is 1. What label would we assign to this using naive Bayes? All right, so, well, for each value of Y, we figure out the probability that you have that Y and A is 1 and B is 1. So let's do this. Probability that y equals 0, a equals 1, and b equals 1. And remember, we're working in this base now. So a and b are independent given y. So probability y is 0, a is 1, b is 1. That's probability that y equals 0 times probability that a is 1 given that y is 0 times the probability that b is 1 given that y is 0. So that's 3/5 times a is 1 given y is 0, that's 5/6, times b is 1 given y is 0, that's 2/3. What's that equal to? We can do some math. So 3 cancels out with 3, 5 cancels out with 5, 2, 6 is 1/3. All right, so I'll just I'll get rid of the workings so that we have, it's terrible. Okay, I'm just gonna get rid of this working and write down 1/3 so that we have room to do the next one. So what about the probability that y equals 1 and a equals 1 and b equals 1? So that's probability that y equals 1 times probability that a equals 1 given that y equals 1 times probability that b equals 1 given that y equals 1. So probability that y is 1, that's 2/5. A is 1 given that y is 1, that's 3/4 from our second table. B is 1 given y is 1, that's 3/4 again from our second table. So what's that equal to? We can kill this 2 with 4 and turn that into a 2. So 3 by 3 is 9. 5 by 2 is 10. By 4 is 40. So again, we're just going to kill this working and write down the answer. So the question is 1/3 bigger than 9/40? Well, 9/40 is less than 10/40, which is 1/4, and a third is bigger than a quarter. So a third is bigger than a quarter is bigger than 9/40. So probability that y equals 0 is bigger. So you would predict that the label is 0. There you go. So now we're going to use Laplace smoothing to smooth out the distributions of probabilities of probabilities of a given y. Because we've got these like 1/6, 1/4. They're very dependent on just happening to only see one thing. We're going to do that. So what is the probability using Laplace smoothing that a is 0 given y is 0? Well, 3, 4, 5, 6. And we see one case of a being 0. So that's 1 plus k, which is 2, divided by, we have 6 real sightings of y, plus we're gonna have 2 imaginary sightings that we haven't yet seen, where a is 0, and 2 more imaginary sightings that we haven't seen, where a is 1. These are called pseudo counts. So what's that equal to? So that's 3 divided by 6, 7, 8, 9, 10, 3/10. And now what's the probability that a is 1 given that y is 0? Well, it's 1 minus 3/10, so that's 7/10. And indeed, we can work it out. So the denominator stays the same. But now we have 1, 2, 3, 4, 5. So 5 plus 2 imaginary counts. So 7/10, just as we calculated. All right. What about if we condition on y being equal to 1? So we're looking at this column, this column, this column, this column. So a is 0. Well, we see one of those. So it's 1 plus 2 imaginary counts, where we see a is 1, divided by the 4 real counts, where we saw y was 1, plus 2 imaginary counts, where y is 1 and a is 0, plus 2 more imaginary counts where y is 1 and a is 1. So that's 3 divided by 4, 5, 6, 7 eighths. So 3 eighths. And probability of 1 given y is 1, well, that's 1 minus 3 eighths. So that's 5 eighths. So hopefully that gives you a bit of a sense of Laplace smoothing. One thing you'll notice is that 3/10 is bigger than 1/6, and 3/8 is bigger than 1/4. So we're moving our probabilities sort of closer to 50-50. All right, I can move that. Right, now we're going to do neural network representations. So here we have a bunch of graphs of functions, and we want to know what neural network-like things can represent these various functions. So let's start off with part 1. So in part 1, you have an output, which is O, and you've got an input, which is X, and you multiply it by some weight, W. So what can you do with this? Well, here, basically all you can do is draw lines through the origin, right? Like if this is X, and this is O, like you can draw various like lines through, but they all have to go through the center, and W just determines their slope, right? Like it's sort of like if you remember y equals mx plus b for like the equation of a line, except like we don't get a b anymore. It's just y equals mx. So those are the only functions you can draw, and the only one here that's like that is a. And yeah, well, none of the others are just straight lines that go through the origin. And how do we make that graph? Well, the graph is 2x, and here, it's wx, so if w is 2, then we can do it. All right, I didn't need this piece of paper, and I'm going to want to scroll up again, so let's delete it. Okay, so next, so you can think of this as our first attempt to create a neural network. That wasn't very good. It couldn't represent very many things. So we're having a second shot. We're introducing a bias term, B, into the graph. So output is W times X plus B. What can you do with that? Well, again, if this is X and this is O, this is just like if you've seen Y equals MX plus B. You do things like this. You do things like this. That kind of thing. You can draw straight lines, and they don't have to go through the origin anymore. So what does that let you do? Which one of these are straight lines that don't necessarily go through the origin? The answer is these two, right? So we can represent A and B. So the answer is A and B. So again, for A, we had W equals 2 and B equals 0, right? With 0 bias, or just back to the normal thing. What about for B? Well, for B, the graph was 4x minus 5. So there we have W equals 4 and B equals -5. All right. So now what we're doing is we're getting a nonlinearity. We're using ReLU. So we have this linear function and then a ReLU. So the ReLU is max of 0 and x. So the graph, just to draw that, this is x. This is ReLU of x. The graph is you're just 0 for all negative numbers, and your x for the positive numbers. That's the graph of ReLU. Now, which functions can you represent? Well, you can't represent A and B anymore, right? Because after you go through ReLU, all of your values have to be 0 or above. So so just any graph that has negative numbers we can't draw. So we can't draw this, we can't draw this, we can't draw this. We can't do that, we can't do that. And what does really do? Like if you think about what really does, it says, or if you think about how this this third little mini network goes, what it does is it takes your input, it draws it through some like affine function, like this, say, and then it like just bends off the negative half, and it says, okay, no, it's not this, it's like this now. So it's taking any, yeah, so that would happen to this one if you had this function here, right? You would cross out all of this bit below 0, and you'd say, okay, that's going here now. And that's kind of all you can do. So what can you do now? Well, the things that look like that are this one and this one, right? So this is 2x minus 5 when x is greater than or equal to 2.5, and 0 when x is less than 2.5, minus 2x minus, yeah, is there some way I can copy this whole thing? What can I do? If I copy that and paste it, paste image. Oh yeah, that's good. That's good. Except it has all the stuff in it. All right. So I'm gonna delete. Sorry about this delay, but hopefully it's worth it. I'm going to select all of this. Select all of this, copy. Now I'm going to, no, that was good. I'm going to paste it here. Make it bigger. Okay. So these are the two ones we could do. So this was 2x minus 5 when x was greater than or equal to 2.5, and 0 when x was less than 2.5. So for C, what we can do is we have w equals 2, b equals minus 5. So that gets you this graph of 2x minus 5. And then you just go through ReLU, so that kills this bit, and that returns exactly this graph. And for D, what we have is minus 2x minus 5 for the bit where it's positive, and then 0 for the rest. Again, how you do that is w equals minus 2, b equals minus 5 again. And after you go through the ReLU, it looks exactly like this. So that's what happens when you just have one ReLU. Now what happens when you have multiple ReLUs? Let's erase all this working out because we're going to need this area. Okay. So we did this one. Now you have two neural networks and you have multiple affine transformations. So what's happening in this network? Well, we're doing, as you can see here, we're saying that f of x w1 b1 equals w1x plus b1, and that's called h here, right? Just the output of this unit here is called h. So h is w1x plus b1. What's the output here? Here, O is this f of h w2 b2, which is w2h plus b2. But h is w1x plus b1, right? So this is w2 times w1x plus b1 plus b2. And if we expand that, that's w2 times w1 times x plus w2 b1 plus b2. And the thing about this is that if you look at that, w2 well, like this is just mx plus b, where m is w2, w1, and b is w2, b1 plus b2, right? But like anything you can do with mx plus b, you can do with this network. And anything you can do with this network, you can do with mx plus b. So it's exactly the same as the affine network, as this one, right? It's exactly the same as 2. So just adding more. So in neural networks, if you just add more layers and you don't use nonlinear functions in the middle, like the Rayleigh function, you can't do anything new. I hope that makes sense. Pardon me. So what are we doing now? Now, we have the same old thing where you have the the affine function, nonlinearity. But now we have this new thing where you're transforming the affine, you're transforming the output of the Rayleigh in an affine way. So what does that do? So if you have a graph like this, so you have some like kind of affine function, right? Like this. And then the Rayleigh kills this bit below and just puts it on the 0 axis. And then this final step, we're again scaling that, we're moving that around. So that would be like saying, you know, maybe it goes like anything you multiply this 0 bit by will remain 0, but you can change where this edge is to, you know, you multiply all the numbers by 10, so they go up a lot, or they multiply them by 0.1, so they go down a lot. And then you can move the whole thing up and down, right? So if you move it up, it might look like this now. If you move it down, it might look like this now. So that's kind of what you can do. You can do any function that looks kind of like that, or, you know, maybe this. And you can put this kink wherever you want. So what's that? We now have access to C, D, and E, right? So how do you do that? So for C and D, we could do that without the final affine transform, right? So for C, we're going to do the same thing that we did in this network right here. So what that was, oh, I guess I got rid of it. But for C, so you had weight 1 is 2. Bias 1 is -5. And then we don't want to do anything, so we're going to multiply by 1 and add 0. So weight 2 equals 1, bias 1 equals 0. And for D, it's kind of the same. So weight 1 is equal to -2, bias 1 is equal to -5. And we don't want to change anything, so we'll set weight 2 equals 1, bias 2 equals 0. All right, what about E, right? So we want to get this minus x plus 3 when x is less than or equal to, when x is greater than or equal to 2, and 1 when x is greater than 2. Well, the flat bit is at 1, which means that bias 2 must be equal to 1. Now, what do we get from the weight 2? Well, weight 2, we need to like when we just have the output of a Rayleigh, the bit that is horizontal, that's like above, right? So we must have multiplied everything by -1 to get this this horizontal bit to be going down instead of up. So if spice2 is 1 and weight2 is -1. So if we draw what this graph would have looked like before doing that, we have the flat bit is now on the origin again. And here at x equals 3, we're sloping up. And before we were sloping down with a slope of 1. So we're sloping up with a slope of 1. So at 4, we're at 1, 5, we're at 2, and so on. So now you imagine, okay, what did that look like before it went through the ReLU? Well, this flat line, before the ReLU was just a line, right? So this would have just gone down, and then we would have killed it to go back up here. But so how far does it go down? Well, here x is 3. So you're going 3 across, and at a slope of 1, you must be going 3 down. So it intersects the y-axis at minus. Oh no, it was, sorry. This was minus x plus 3. Sorry. This was at x equals 2. X equals 2, right, is where all things were changing. So 2, 3, 4. So you go across 2, so you must be going down 2 if your slope is 1. So the bias 1 must be -2. And then what's the slope of the original line? Well, it's just 1. And you can, that was a sort of convoluted explanation. I hope it kind of makes sense. If it doesn't make sense, you can at least like try and figure out what what this does at like 4 and 0 and 2 and 5 or whatever, and check that it agrees with the graph here. All right. So now we're doing part 6. And I'm gonna bring the list of functions down. Can I just paste? Hope you enjoy watching me learn how to use Notability. Okay, yes, I can. So now we want to know what we can do with a third ReLU and third affine transformation. So there were kind of two things. Yeah, what could we do with the just until here? Well, we could get things like this, or like this, or like this, or like this, right? And now with another ReLU, we're flattening off everything below 0. So if we imagine the x-axis is here, we have the ability to like get some things to be down to kind of have like 3 parts, like 1, 2, 3. And then once you can do an affine transform, you're moving them around and you're sort of sloping them. So here we can have bits that are 2 parts or 3 parts at 0, and they can be sloped however we want, and they can be anywhere in the plane that we want. So how does this work? What can we do with this? Well, notably, when the things that have 3 parts, they can only be flat here and here. We can't get something going like that, because you have this ReLU and you go through a linear function, and if you're all 0, then when you add something, when you multiply it by something, you're still 0, and then you add it and you're just moving it up and down. So it's always going to be like a flat line. So you can't get this. So what things can you get with this? Well, you can get all the things that you used to have, because the W2 could be 1 and B2 could be 0. But you can do, well, it's a little bit more complicated because things underground. You might have to move it down. Yeah, you could set W. Yeah. Sorry. You could set this to do nothing, and then this looks just like the network in question 5. So you can certainly do C, D, and E. So C, D, and E. But this kind of Z shape, we can also do that. So the answer is C, D, and E, and F. And how do we do C, D, E, and F? Well, let me show you. So for C, we copied the old weights, but our old W2 and B1, we're going to move that to W3 and B3. So for C, we have W1 is 2, B1 is -5, W2 is 1, and B2 is 0. And then W3 is also 1, because that's what C said. And B3 is 0, because that's what C said. For D, we're going to copy W1 and W2 from part 5. So W1 is -2, B1 is -5, W2 is 1, because that does nothing, B2 is 0, because that does nothing. Then W3 is whatever W2 was, which in this case is also 1. B3 does whatever B2 did in the old part, which is 0. Okay. E is a little bit more interesting. So here W1 is 1 as an E, and B1 is -2 as an E. Now we're doing nothing with W2 and B2 again. So W2 is 1 and B2 is 0. But now W3 is what W2 used to be, so -1. B3 is what B2 used to be, which is 1. Now what about F? F is kind of the most interesting one here. So what are we doing with F? So we can see that after you went through the ReLU, you have this flat bit here, right? And it's located, we're going to think of that as the thing that went through the ReLU. And it's located on the x-axis, which means B3 must have been 0, because it didn't go up or down. And because this bit is flat also, what that means is that W3 must have been equal to 1. If W3 wasn't 1, we could have had something like flat, right? Like you multiply all these by some. Oh, that's not actually true. No, it was always going to be flat. Never mind. My apologies. But we can just think of W3 as 1, and that's going to serve us fine. So what that means is that before we went through the ReLU, we were this function that was like, it was 3 here until you reach 0. And in this case, it's 3 minus x, so it goes 3 here. So that looks like you had something that went through ReLU that got moved up 3 and then got multiplied by -1, right? Because if we move this down 3 and then multiplied by -1, then you would get this graph, right? So this black thing, this intermediate black thing, it looks like it was something through ReLU, then you added 3, then you multiplied W2 by minus, W2 is -1, you multiplied it by -1. And now you have this good old ReLU function. This, you can see this slopes down with a slope of 1, so this slopes up with a slope of 1. So this is pretty simple. This is just, it's got no weight and no bias, really. W1 is 1, B1 is 0. So that's F for you. But yeah, you can see that if we had, like, if you had this this black thing here, right? So we took the ReLU of it. Yeah, you could have multiplied it by something and moved it up, and that could have changed you to this, or it could have been more like this. That could have been fun, except this would still go down to this point here. All right, so that's part 6. And one thing you should be noticing is that we're adding more layers and we can do more things. So that's pretty cool. What about question 7? You have one hidden layer, but it's a big layer. So you have this input that goes in 2 places, right? And then there's an affine function here, an affine function here. And now you have an affine function of both of these inputs that's weighted by H1 is weighted by W3 and H2 is weighted by W4, and you're adding this bias, and that's your output. What can you do with that? What can you do with that? All right, well, let's do some math. And we don't have a lot of space to do the math, so I'll just do it here, but it'll be a little bit sad. So what's H1? So H1 is W1x plus B1. H2 is W2x plus B2. And O is W3H1 plus B plus W4H2. So that's W3 times W1x plus B1 plus B plus W4 W2x plus B2. But here we can just group terms, right? We can say this is x times W3 times W1 plus W4 times W2 plus B1 W3 plus B plus W4 B2. So again, this is just an affine function of x. And the secret is, if you do an affine function over and over and over again, you don't get anything that isn't an affine function, even if you do it kind of weirdly, as in this question. You just always get an affine function. You can't escape if you keep doing affine functions. So what can you represent with affine functions? Well, let me just remind ourselves what the networks are. So which of these are affine functions? The answer is just the first 2, the boring old first 2. And how do you, what are the numbers to do it? Well, that's a little bit, we won't go into that for the meantime, because it's kind of tedious and boring. All right, now you're adding a nonlinearity between the 2 affine layers. So you have an affine function, So you have this H1 prime and H2 prime. And these are basically like hidden neurons in a neural network. But this time we have 2 of them. And now we have them go through another affine function. What can we do with that? Well, first of all, we can't we can't do anything. This G, right? We can't do that because all we're doing is like, we're doing affine functions, and then we're like bending the bottom, bending all the negative stuff to be 0, and then we're doing another affine function, we're bending stuff to be 0. So we can't get this like smooth curve that G has. But we can do a lot of things. So any network from 5, right? So back when we had just this one hidden unit and an output, we can do that by setting W4. So this weight here that takes H2, we can set that to be 0. So we can ignore this and just imagine you have affine function, ReLU, affine function. So anything you could do in part 5, you can still do now. All right. So what else can you do? So what are H1 prime and H2 prime? So they're these ReLUs, right? They're outputs of ReLUs. So H1 prime might be something like this. Let me get axes. I need more space. So H1 prime might be something like this, and H2 prime might be something like this. So you can, so there are these independent functions with flat parts lying on the x-axis, and there's a part with some slope. Or maybe they don't have to be pointing different ways. You could use this one and this one together, and then you have a affine combination of them. So you'll take some sum of these. So if you were taking sum of this one and this one, the thing you would get would look like this. But you could also take you could do this one minus this one, right? In which case, so that would look like this one. Then you subtract off the second function and you go down instead of up. Or you could, if you add this to this, then you get like, you go up here and then you go up like way faster because you're adding both of them. So you're doing these like, you're multiplying, you're adding, and then you're you're doing anything you want. Not anything you want, just multiplying and adding, and like then this flat bit down here, you can move that up and down by using the bias term. So you can kind of grab this graph and move it up, or you can move it down. All right. So so we said that we could do CDE. Yeah, CDE and well, CD and E we know how to do, right? So I'll move this whole thing, this big mess down a bit. Okay, so C, D, and E, let's just check those off. So okay, no, we can't do this. We know how to do C, we know how to do D, we know how to do E. But we like to do F and we'd like to do H. And can we do A and B, right? Well, let's do A. We have this linear line. Well, here's what we can do. We get a ReLU, the output of a ReLU. So it'll look like this, right? So this is 2x, you put it through ReLU. So that's your F1. Then your F2 is minus 2x, but then you put it through ReLU. And then if you do the black minus the orange, you just get exactly this. And that gives you A. What about B? Well, it's just the same thing, except the y-axis is here now. We know how to, we can put ReLUs with their, we have these affine functions that have some intercept, put them through ReLU, so they look like the black and they look like the orange, and the red looks exactly like this. So that's how we do B. All right, next we want to know how we can do F. How can we do F? So let's erase this to give us some working room. So the way we're going to do it is we'll have a ReLU for the left part like this. So that's going to be doing this. And then our second ReLU is going to be 0 all the way here and going up like that. Sorry, I should draw the second ReLU in different color. So here's green, and it's a dotted line in case it's hard to see what's black and what's green. So this is the second output of a ReLU, right? Now I'm going to do the black line minus the green dotted line, right? So what does that give you? So that gives you, you have, everything to the right of the x-axis just stays the same as it was. But then here, you're adding you're starting from here, you're going up a bit because of this, but then you're subtracting just the same amount off. So you're staying constant, just like a little bit above. Hopefully that makes sense. It's like this is, this is minus 3x plus, or let's just say this is a minus x plus 3. This is minus x. Well, minus x plus 3 minus x is just equal to 3, right? So for all of this part, you would be here. And that's how you do part F. That's just how you do that. Now, how do you do H? And I'm sorry, I'm not giving numbers here, but hopefully this will help you figure out what the numbers would be. Like to figure out, how do you get a ReLU that looks like this? Hopefully the previous part gave you a sense of how you would find out those numbers. Okay, so how do you do H? Let's call this and draw the axes again. Well, so at H, starting, so less than 0, we're going down a bit, and starting at 3, we're going up with slope 3. So we'll have one of these curves like this. So this is a ReLU that is going, this is y equals ReLU of 3x minus 9. So you have this slope of 3, and then you're flat here. Then our second function, which is going to be pink, and it's going to be sloped. So starting at 0, you're going down with a slope of 1/2, and then you're ReLU'd so that you're on the x-axis. So this is ReLU of negative 1/2 x. All right, and now you do, if the solid black is y1 and the dashed pink is y2, if you just do y1 minus y2, that, let's do that in green. So that's going to be same here, right? Because the dashed is 0. Same here, because the dashed is 0. But because we're subtracting, where the dashed went up below 0, this is going to go down below 0 at the same slope. And that gives you exactly H. So what's the lesson of the story? Well, the lesson of the story is as you add more layers, And especially if you have hidden layers, like lots of hidden layers you can combine in clever ways, that makes you, that gives you more power to represent more functions. So bigger neural networks can represent more functions. But it turns out you can still train them just fine. And that's like, if you've heard people talk about deep learning, right? What's deep? What's deep about it? It's not, well, it might be profound, but it's not called deep because of that. It's called deep because you just have a bunch of hidden units in a row. You know, you'll have units here, and they're feeding into, you know, they're feeding into a bunch of units here, and they're feeding into a bunch of units here, and they're feeding into a bunch of units here. And you just keep on applying, like, affine transform of these plus, and then you put it through a ReLU. Affine transform of these again, put it through a ReLU, and then, okay, now do it all again. Okay, you've got outputs, now do it all again. That gives you the power to represent a whole bunch of functions, as you've hopefully seen. And, you know, eventually, like, this thing that we couldn't represent, log x, you saw how as we had got more hidden layers and more nodes, we could do more kind of linear functions. You can imagine, you know, you could do like this, 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 this. We could eventually approximate it. This should actually not be so steep, but we could eventually approximate it with just linear bits really, really, really well, the more we had. And in your project, I hope you're doing project 5. It's a fun learning experience. You know, you could just do it on your own time if you don't want to submit it for credit. But in your own project, you can see that you can approximate the sine function really well. All right, so that's the end of today's worksheet. I hope that made sense. The end of the semester is coming up soon. So I hope you've enjoyed the course, and I hope you do well in the upcoming final exams, and I hope you learn well in these upcoming lectures. I'll talk to you again next week.